Alright, good morning ladies and gentlemen. I hope you all are having yourself a wonderful Thursday. Today, we're going to continue to talk a little bit about the probability of independence, dependence, and conditional probability, but in a new light, because I want us to talk about the probability of complements. And not that type of complement you're thinking about. That's a complement with an I. We're talking about complements with an E. The opposite of what you think or what is. Now, another way to think about this, a complement is something that makes up the entire whole of something. Or we could think of like a complement would be the thing that goes along with it to make it whole. Like if there's rain, well, there has to be not rain. If there's a color red, then there has to be colors that are not red. And that's really what is going on here. It's the opposite, or it is the not of a specific event. And it's often written as, if I have some sort of probability of some event, well, its complement has to be the probability of the event, either with this, meaning like a little dash, or sometimes you see it with a C, meaning the complement. Now, the mathematical portion of it is that a probability plus its complement is equal to 1, meaning that it makes up the whole. If you have a probability and its if you have a probability of an event and its complement, and you put them together, you have all the probabilities that can exist. Like suppose that this is a cookie. And it's not a good cookie. Well, who knows? It's a snickerdoodle. Those are my favorite cookies. And let's say that this is A. That is a part of the cookie. Now this would have to be the complement of A, because it's what makes up everything else. You have A and you have not A. When you put those together, it makes up the whole. Just like if you break a cookie in half, well, you have a portion of the cookie, and then you have the not portion, the other portion of the cookie. Let's see this in action. If a chance of rain is 0.45, what is the chance of it not raining? Well, if I know that everything has to add up to 1, the chance of rain and the chance of not rain have to add up to 1, well then 1 has to be equal to 0.45 plus, let's do it, our complement, well, minus 0.45 on both sides, and that's going to be 0.55 is equal to the probability of not rain. So I hope that makes sense for you all, that if it's the mathematical complement, it has to be the other portion of it. Now let's look at this one. A wallet contains 2 5s, 2 10s, and a 20. What is the probability of drawing 1 and not getting a 5? Now it might be initially difficult to figure out, okay, what's the probability of not getting a 5? You have to calculate everything that's not a 5. Sometimes it's just easier to find the complement and then just do the opposite. Now, if we know all probabilities have to be E over T, we want to find the probability that we're going to get a 5. Well, how many 5s are there? There's 2 5s. How many bills are there in total? Well, there's 5 bills. Well, that's pretty easy. The probability of getting something other than a 5 complement has to be the other portion, 3/5. It has to make up the rest of the fraction, because 2/5 plus 3/5 would obviously give us 5/5, which is just 1. Let's move on. Now, if you were in my statistics class, you've seen this example probably 3 different times, because it's just repeated over and over. In a sample of 50 people, 21 of type O blood, 22 of type A blood, and 5 people of type B, blood and 2 people have type AB blood. Find the following probabilities. Find a person does not have type AB blood. Well, this one should be pretty straightforward. The probability of someone having type AB blood. My mouse is really not wanting to cooperate today. Well, someone having type AB blood, that's just 2 out of 50. Well, the probability that someone does not have AB blood, well, that has to be the opposite. That has to be 48 out of 50. Because you put 2 and 48 together, boom, you get 50. So, a person does not have type A or type O blood. Now this one's a little bit more tricky. You have to find the probability of type A or the probability of type O. Because type A or type O, that's really a union. Probability of type A or type O is equal to the probability of A plus the probability of O. Now you might think, wait, why aren't we subtracting the intersection? Well, there's no intersection between type O and type A. There's no AO blood. There's AB blood, which would be an intersection. Actually, no. This is all mutually exclusive. So there's type AB blood is not type A, and it is not type B. So there is no intersection, so you don't have to worry about subtracting an intersection. Well, what's the probability of type A? 22 out of O. Let me go back and simplify that later. 22 out of 50. And type O is 21 out of 50. That means total out of this, its union is 43. Whoa, don't know what happened there. Its union would have to be 43 out of 50. And so the probability of it not being the union, anything other than O and A, would have to be 7 out of 50. Now, this should make sense because what's 5 plus 2? 7. And if it's not type O or type A, it has to be type B or type AB. So, this is our answer for the probability of someone does not have type A or type O. Now let's go back to this. 48 out of 50 is pretty neat. It's pretty direct. Like 48 out of 50 people have do not have type AB. But it's not a simplified fraction. It should be 24 out of 25. Alright, now let's go back to a specific example. Let's go back to exclusivity, complements, and independence. Suppose a cooler is 6 Powerades and 3 red, with 3 red and 3 blue. Further suppose that the same cooler is 5 Gatorades, 3 red, and 2 blue. This should look like a pretty similar example to what we did yesterday, because it's the same data. Determine that the probability that you reach for a drink and the second one is a blue Gatorade. Now, if we look at this should just be like the one from yesterday. Okay, we have to consider 2 cases, one where it is a blue Gatorade and one where it's not a blue Gatorade. But the thing that's different is because this one is dealing entirely with complements. Let's suppose we have 2 cases. Case 1 and case 2. Because we're reaching for 2 Gatorades, right? Well, the first drink could be a blue Gatorade, or it cannot be a blue Gatorade. The same thing applies to the second drink. It could be, that one has to be a blue Gatorade, so we know exactly what we want for the second one, but we don't know what we could get for the first one, so we have to consider multiple probabilities. So, let's say the case number 1 is where we don't get a blue Gatorade for the first one. How many drinks do we have in total? In total, we should have 11 drinks. How many of them are Gatorades? Well, specifically, how many of them are blue Gatorades, since that's what they're looking for? 2. Well, how many of them are blue Gatorade complements? Well, if it's not 2, it's got to be 9. So what if our first drink is not a blue Gatorade? Well, that's 9 out of 11 times 2 out of 10. Now, why is it 10 under the second one? It's because you've already picked a drink, so therefore your other number is different. Now, if I multiply these together, that should get me 18 out of 110. And if I divide that by 2, that's 9 out of 55. And that should be our final answer on this one. Yep. So the probability of getting a blue Gatorade out of case 1 is 9 out of 55. Now let's consider case 2. What if both drinks we grab are blue Gatorades? What is that? Mountain Berry, I think, or something? They're always named something weird. Alright, so, well, there are 2 blue Gatorades, and in the beginning there's 11 drinks. Well, after we've already picked one, there's only 1 blue Gatorade left out of 10. And that is a 10, that's not a 16. Yeah, it's a 10. We multiply those together, and that's going to give me 2, I almost said 3, out of 110. Well, if we simplify that down, that's going to give us 1 out of 55. So we have our probability for case 1, we have our probability of case 2. We're going to add them because we have to consider both cases, because it's the union. It's actually a union between both cases, and that's going to give us 10 out of 55, because it could be case 1 or it could be case 2, and there are no intersections between the two. So our answer is, if we're reaching for 2 drinks, the probability that the second one is a blue Gatorade is 10 out of 55. That's not really that bad. It's a little over 20%. Actually, no, take that back. It's a little under 20%. Yeah, it's a little under 20%. I don't have a calculator on me right now. Alright, so the first DC statistics class, there are 6 girls and 10 boys. The second DC statistics class, and this is from Manassas High School, there are 8 girls and 6 boys. If 2 students are picked at random, what is the probability that the second one will be a boy from the first class? Well, how many kids are there in total? In total, there are 16 in here and 14 in here. So in total, there are 30. Well, how many, we have to consider how many boys from the first class. Boys from the first class, well, first class there are 10 boys. How many people are not boys from the first class? Obviously 20. So 2 cases. I'm going to be wrapping this up quick. And the same, what if your first one is where it's not a boy from the first class? I miss my DC statistics class. They were very good, they worked very hard, and it was always fun to work with them. I do miss them. I miss teaching. I miss teaching the class I'm teaching right now. Alright, second one. It's going to be 10 boys in the first class out of 30. Oh, this should not be out of 30. That should be out of 29. Because you've picked a boy, you can't pick that same boy again. Alright, ladies and gentlemen, once you multiply those together, simplify, and then add them together, your answer should be 29 out of 87, meaning if you were to do this experiment 87 times, you'd probably pick a boy out of the first class second 29 times, which is pretty good, actually. That's a pretty high probability considering things. Ladies and gentlemen, I hope you all have yourself a good Thursday. I've got to sign off for now because I'm going to be late for one of my math meetings. Have a nice day.